All right, so picking up from last time, what we're going to be covering today is the second part of this title, which is homogeneous equations. And the first thing we have to talk about as we get to that slide is what in the world we mean by that. So a homogeneous function of degree n is a function that's not separable. Okay, if we have separable functions, we already have a way to handle them. So they're not separable in x and y, but they can be made separable with a change of variables. Okay, so we're going to be able to do a change of variables, which you guys know how to do, right? Use substitution kind of thing, change of variables. And the change of variables is of the form f of tx, ty, equals t to the n f of xy. Do I not have n's on anything yet? Oh, I didn't write it down on here, did I? No. Well, let's just do that right now. So in other words, if we replace x with tx and y with ty, it is equivalent to multiplying by some power of t outside of my function f of xy. So once we've done this substitution, we will be able to separate our variables. That's the goal. Okay, do the substitution, then we can use separation, everything we did before. And by definition, then, a homogeneous differential equation is an equation of the form m of xy times dx plus n of xy times dy equals 0, where m and n are homogeneous functions of the same degree. And the degree part is this degree up here in this exponent. Okay, so this one right here, if I were dealing with this, I would call this a homogeneous function. It would have degree n. Okay, so whatever the variable or whatever the exponent is that is able to be pulled out of the f of xy function, after I do this, that would be my degree of my function. And all of that just sounds like a bunch of words. So let's do one so you can see what it means to do this, okay? All right, so we have a function f of xy, and all we're asked to do here is the first part of this last slide. Okay? The first part of this last slide talks about whether or not this is a homogeneous function and what degree it is. So this one says, determine if the function is homogeneous, and if it is, determine its degree. So this is not a homogeneous differential equation. We're just talking about a homogeneous function on this one, okay? All right, so we have a function, f of xy equals xy over the square root of x squared plus y squared. And to decide if this is a homogeneous function, what we want to do is the left-hand side of what you see back on this slide before. We want to substitute in tx and ty for x and y. Okay? All right. So everywhere we have, and I'll do a slightly different color just to show that we're doing a slightly different function. Let's see if it shows up differently. Can you see the different color up there? It is a brown. Let me try something a little bit different, more than that, so that it's... Sure, we can do red. There we go. Okay. The colors don't show up as clearly on your projection as they do on my iPad, so I'm never really sure what's going to happen until I put it up there. All right, so we're going to plug in tx and ty for x and y. So I've got tx times ty. Whenever you're working with t as well, be careful they don't look like plus signs. Okay. Over the square root of tx quantity squared plus ty quantity squared. So far, so good? Okay. Well, you'll notice on the very top then I've got t times x times t times y. There's a way I can write that simpler. How else could I write the numerator? T squared xy, which starts to make me wonder, is this homogeneous of degree 2? Because it's got a t squared, right? Don't jump the gun on that. We still have to simplify the denominator to see if that really is what's going to happen. All right, so my denominator, I actually end up having t squared x squared plus t squared y squared. Everybody with me so far? All right, I think I have another slide. Let's see. Awesome. Okay, so in that denominator, ignore the square root for a moment. What do the two pieces that are under the square root have in common? a t squared. So what I'm going to do is I'm going to take that denominator and I'm going to factor out the t squared. It'll still be underneath the radical, but I'm going to factor it out in front of the x squared and the y squared. So right now I have t squared xy over the square root of t squared and x squared plus y squared. My goal is to somehow get this whole expression to look like the one I started with a t to a power in front of it. Okay, so my goal is to turn it into this piece with t to some power n out here in front. That's what I'm looking to do. Okay, and if I can do that, it is homogeneous, and if I can do that, whatever that exponent is my degree. Right. All right, so noticing this, one of your properties of radicals that you learned a long time ago is that if you have multiplication underneath a radical, you can separate them out to be underneath their each individually owned radicals, like this. So the property that says something like this, the square root of AB is the square root of A, the square root of B. It doesn't work for addition, doesn't work for subtraction, but it works for division and for multiplication. So we've got multiplication here, we can use this. All right, so then that's good because then I've got a square root in the denominator that looks exactly like the original square root in my denominator from my original problem, right? And what is the square root of t squared? That's t. Okay, now what? So the t that I just put in the denominator and one of the t's in the numerator can reduce or cancel. That leaves me with one t that I can write in front all by itself, right, because it's multiplied, with the xy and the square root of x squared plus, I have a really difficult time writing 2's very clearly, that's better, plus y squared. So is this a homogeneous function? Yes, it is. And as a matter of fact, what you see now here is a t, and you see this original function that I was dealing with right here, which was originally called f of xy. Right? That blue is really not readable, is it? Let's try a little bit darker. That one's better. Okay. But I have a t in front. I've got the f of xy after that. So it is homogeneous. So this is homogeneous of degree what? Degree 1. Because I don't see it here, but we haven't understood 1 as the power of that t. So this is degree 1. Okay, so this is algebra, right? There wasn't any calculus in that. That was all an algebra exercise. But we need that in order to be able to decide information about homogeneous differential equations. So let's take a look at how that's going to be handled with one more theorem for the day. Theorem 6.2 talks about this change of variables issue. So this is a change of variable for a homogeneous differential equation. If m of xy dx plus n of xy dy is 0 is homogeneous, then it can be transformed into a separable differential equation by the substitution y equals vx, where v is a differentiable function of x. Now you may think that there's one reason that this last problem has so much space. It's just the last problem and there's that much space left. But in reality, take a look. Okay, this is a really lengthy problem, so write, not microscopic here, but you need to write kind of smaller. You're going to be able to flip over your paper or something like that. This is going to take a little bit of space to do this problem, okay? All right, so we're taking a look at this equation, y prime, which is a differential equation, because it's got a prime in it, right, equals x squared, plus y squared over 2xy. So the first thing I'm going to have to do is that I have to get it to look like this form, because I need to be able to identify what the m and the n functions are that we're talking about. So far, so good? Okay. This one says solve the homogeneous differential equation. So the first thing I need to do is I need to actually, and it isn't even so much getting it necessarily into the form where that's equal to 0, but it's where I've got the dx on one side and the dy on the other side a little bit too. So let's take a look and you'll see what's happening as we're working. Okay, where's my black? There we go. All right, so the first thing I'm going to do is I need to get this to be written so that I have a dx and a dy in the problem and I don't have the denominator. So the first thing I'm going to do is I'm going to multiply the 2xy to the left. So this is dy dx right here, right? I'll leave the dy on the left, and I'm going to have x squared plus y squared, and I'm going to move the dx to the right. Clearly, I could add or subtract. I could get them on the same side now, right? Where I have some function with a dx and some other function with a dy. And if I wanted to confirm that these each individually, that is the 2xy and the x squared plus y, were both homogeneous, I could do that. I'm not asked to do that in this problem because this problem tells me that this is homogeneous, doesn't it? Solve the homogeneous differential equation. So I don't have to verify that it really fits the form. However, you should look at that and think very clearly 2xy should. If I replaced x and y with tx and ty, yeah, the factor would come out as t squared, wouldn't it? I'd have a 2 and a t squared and an x and a y. And if I replaced the x squared with tx and the y squared with ty, and squared each of them individually, same thing. In fact, we just did that denominator, didn't we? And aside from the square root, it pulled out as t squared. So these are both homogeneous, and they are both of the same degree. They're both degree 2. Okay? What this theorem above, though, tells me that I can do is that I can actually take a change of variables, and my change of variables is going to be letting one of the variables, well, it said, letting y equal to vx. Okay? So right here, we're going to let y equal vx. And believe it or not, even though it's not sort of obvious at the moment, obvious in a moment it will be, that we need dy, right? That is, we need the derivative of this situation. V is not just a number, though. It's not a constant. Look back over here at this theorem. It tells you that v is another function of x, right? So what we really have is we have two variables, v and x, that are multiplied. And if I want to take the derivative of them, what is the overarching rule that's going to be used on the right-hand side? No. Product. Because I have a v multiplied by an x. This is the product rule. Okay, so the product rule says take the derivative of v, and what is the derivative of v? dv. It'll be dv. It would be 1 if it were just the x, but these are all in terms of x, okay? And then I have, and then I've got times x, right? So let me write the x in front of this. So x dv. Plus, and then I need the other half of that, which means writing down my v and taking the derivative of x, which is going to be dx. So I'm running out of screen space over there, but let me move it a little bit. Okay, I don't want to move the y. Okay, I'm not having any luck moving it. All right, so I've got dy is equal to x dv plus v dx. Okay, that's the product rule in a nutshell anyway. Now, the reason that I need that is because if you look back in your equation, do you see how your equation has x, y, a dx, and a dy? It has 4 different unknown quantities, x, y, dx, and dy. 2 of them have to do with y. So if I remove y by substituting in vx, I can't have the dy still in the formula, right? That's not going to work. So I need another expression for dy that eliminates the need for having a y in the problem because I'm eliminating my y. So over here back in my problem, I have 2 times x times y, which is vx, times dy, which is x dv plus v dx. And this is going to feel a little bit awkward at first, but we're going to go ahead and distribute the right-hand side in a moment too here. I think maybe I'll wait a step to do that. Let's go ahead and substitute my y in, and then I'll distribute, because we're going to distribute the left too. All right, so I've got x squared, that's fine. And then I've got y squared, but y is vx. So this is the quantity vx squared. And then times dx. Is everybody with me so far? Okay, so we're going to be doing a little bit of algebra now. Okay, so we're going to distribute what we can, and we're going to collect all of the terms with one thing on one side and so forth. We've actually made all of the steps we need to be able to separate this thing now. I'm going to be able to separate all the x's on one side and all the y's on the other because of this substitution. Now, it doesn't really look like it yet, but it will as we continue to work with it, okay? So on the left-hand side, this piece right here is actually 2x squared v. Agreed? So I'm going to multiply 2x squared v through the next set of parentheses. So if I multiply it by x, I get 2 what? X cubed v dv. Now I need to multiply it by the second piece, the v dx. So I've got again a 2, and then what?
So 2x squared v squared dx.
Perfect. All right, on the right-hand side, I'm going to distribute the dx through. So the first piece I've got is x squared dx. The second piece I have is what? Yes, and I'm going to put the x at the beginning just because I've already got the x at the beginning on the terms on the left. So I'm going to write it as x squared v squared dx. All good? Okay. Think about your separable functions that we worked with last time. One of the issues that you had to have is you had to have only one dx and one dy in the problem. We didn't really say it, but that happened, didn't it? Yeah, that wasn't by accident. So I need to get all of the dx's on one side and all of the dy's on the other side, and then I'm going to be factoring back out what I just multiplied out. I only have one dv, so it's actually going to stay put where it is. 2x cubed v dv. And then the other piece that was on the left-hand side right here, it is going to move over to the right-hand side, okay? So one piece I have over here is x squared dx. Another piece I have is x squared v squared, but I'm going to be moving over a 2x squared v squared with what operation? Subtraction. So I've actually got x squared v squared minus 2x squared v squared, which means I really have what? I have negative 1, or just negative if I want to write it that way. X squared v squared dx. How are we doing? We okay? All right. Now it's perfectly fine that the left-hand side has the x cubed, the v, and the dv all in it. The right-hand side though needs a little bit work because I still have 2 dx's. So in essence, I'm going to factor out the dx, and I'm going to factor it out at the end. Okay, so I have the dv all on the left, and I've got the dx all on the right, but I still have x's and v's on both sides, correct? And I shouldn't if I'm going to continue through the problem. Somehow I've got to move those around. Notice on the right-hand side, we've still got a little bit of work to do because what's in that parenthesis currently is incomplete. Or not incomplete, but it can be simplified, I should say. Notice what's inside of that parenthesis has something in common to both pieces. What do you see? I think that square didn't come through when I copied and pasted. What's common to both pieces inside that parenthesis? X squared. So I could pull the x squared out in front. When I factor an x squared out of x squared, that leaves me with 1. When I factor an x squared out of x squared v squared, that leaves me with v squared. The sign in the middle stays. It's negatives. This is negative. And then on the left-hand side, I still have 2x cubed v dv. All right, I need to get everything with v on the left, everything with x on the right. How am I going to do that? Okay, Cameron, tell me one division that I need to make, just one of them.
Move the x cubed over to the right side.
Okay, so if I divide both sides by x cubed, I will no longer have any x cubes on the left. I will still have some x's on the right, though. Now what? What else do I need to move? Someone else besides Cameron. Yes. So I'm going to divide by 1 minus v squared, which will mean, again, on the right now, I no longer have any v's. But on the left, I still have some v's. So simplifying what I have here now, I have 2v over 1 minus v squared dv equals, and how is the x squared over x cubed going to simplify? 1 over x. I'm going to put my dx at the back. You could put it on top if you want. I don't need this right here. That's where it was supposed to be, was down here. There we go. V is all on one side, x is on the other side. I've separated them, right? So I can do an integration now. I can integrate both sides. Let's start with the right-hand side because it's the easiest. What is the integral of 1 over x dx? ln of absolute value of x, and I'm going to have a plus c somewhere, so let's just put it on the right-hand side as that's what we've mostly been doing recently too. Actually, we'll call it c1 because we're going to need to change it in a minute. So, how about the left-hand side? How am I going to integrate 2v over 1 minus v squared? Okay, then what would du be? Close. Negative 2v dv, and actually I have the 2v dv in the problem, I just don't have the negative, correct? So I've got this actually going to be negative integral of 1 over u du, and what is the antiderivative of that? Yeah, close. Negative the actual log of the absolute value of u, yeah. All right, so we've dealt with this last time. We saw problems almost identical to this, right? What did we do at this point? Remember, our goal is to solve for y, or in this case, the way I've got it set up to solve for u. What did we do?
You want to substitute first, or do you just want to...
Yeah, at some point I have to substitute. Do you want to substitute now? We can.
But raise to e.
Yeah, we're going to raise to e at some point. I guess let's go ahead and substitute now since you mentioned it, Cameron. So this is the natural log. My u...
We're going to do both.
Yes, we will eventually. Let's do it one step at a time so I don't lose anybody, just in case somebody didn't catch that, okay? My u is actually 1 minus v squared, correct? But the problem didn't start out with v in it either. It started out with a y in it. How is v related to y?
Y over x.
Mm-hmm. So over here, if y is equal to vx, then v is equal to y over x, right? So my replacement over here for v is y over x. This will be quantity squared at the moment. And then equals the natural log of the absolute value of x plus c1. We're getting closer. Let's see. I do need to put the e in there at some point, but I definitely can't have that negative in front of it and simplify with the e as a base. So the negative that's in front of the natural log on the left-hand side needs to be altered. How do I get rid of the negative that's in front? Any thoughts? What if it were a 2 that were in front? What would you do? If this said 2 natural log, what would you do? Right. And we can do that here too, can't we, Hannah? We can. This isn't a 2 in front. What is the number that's in front of this? This is a -1, right? So I can take this -1 and I can make it the exponent on this inside of the log. Before I actually make it the exponent, I want to clean up the inside of the log because the inside of the log right now has got some subtraction and some squaring that's a little bit cumbersome to keep writing. So to start with, I would need to express that as 1 minus y squared over x squared. There's a delay sometimes on these screens. So, and then this equals, of course, the natural log of the absolute value of x, not squared, plus c1. So I can get a common denominator inside and simplify so that this ends up being rewritten as x squared minus y squared over x squared. Everybody good with that so far? And then, just like we were talking about a minute ago, this can become negative. What happens with a -1 exponent? What does it do to fractions? It flips them. It has a reciprocal, right? A negative exponent makes a reciprocal. So all I'm going to do is to change this to being x squared over x squared minus y squared. And then I can do the base e. Okay, so on the left-hand side, I end up with x squared over x squared plus y squared. On the right-hand side, remember what this does is this actually applies, because this is addition, it's equivalent to this saying e to the ln of x, e to the c1. Remember that from last time? Yes. It is negative, you're right. Thank you. And then on the right-hand side, the e ln, this piece right here, becomes just x. No absolute values needed any longer. E to the c1 is just a constant, right? I know they both look like letters, but they're also letters that are actually representing a number. C is a constant, E is a constant where we know the number value for it. So I'm going to rewrite that as plain old C, and I'm going to write it in front of the x. And we're still working algebra here, aren't we? The algebra is far more intense on this problem than the calculus could ever hope to be. Right? This is not intense calculus. This is very intense on your algebra skills, though. So I need to solve for y. What am I going to do?
Divide cx over the other side and multiply x squared minus y.
Okay, before I divide cx, I'm going to just, well, I guess we could do that at the same time. Sure, why not? Okay, so Cameron wants me to divide both sides by cx, which will be fine. And you want me to multiply the x squared minus y squared to the right at the same time? Sure, that'll work. So on the left, this cancels. On the left, what are we left with? What is x squared over cx? Let me rephrase it. Does x squared over cx simplify?
It's just x over c.
Yeah, it's x over c, right? And then on the right-hand side, I now have x squared minus y squared. Now what?
Subtract x squared.
Okay. Then,
Multiply by 21.
okay, so I need to change everybody's signs, right? That'll turn the left-hand side into x squared minus x over c. And the right side will just be y squared. Last but not least, what do we do? Right, so this is y equals the square root of x squared minus x over c. Or you potentially could see this written, of course, as something like cx squared minus x over c. Something of that variety. If you were trying to figure out what c was in relation to the variables you were given, you could figure out what c is. You could solve the equation for c, right? Back over here when we had the pieces that are in black that I just shaded over, we could solve that for c, couldn't we? Yeah, if we were asked to solve for c, we could do that. If we were given a point and asked to find a particular solution, right? Given if you were told something like, when x equals 1, y equals 7, we could plug that in and we could solve for c, and then we could actually find this exact expression without the c involved too. Okay, any questions on this? All right.